Hello, everyone. Welcome to the lecture series for PHYCHEM or Physical Chemistry for Engineers 1. Now, our next topic is about perfect gas. After studying this module, you should be able to accomplish the following outcomes. One is to express through mathematical equations and graphs the behavior of gases as described by gas laws and predict changes in pressure, volume, and temperature. Second is to state and use the general ideal gas equation in calculations, including determination of molar mass. And lastly, define partial pressure of a gas and relate it to the mole fraction of the component. Now, we all know that the three basic phases of matter include solid, liquid, and gas. Now, for solids, so they do not fill the container and do not conform to the shape of the container, the particles are very closely packed, and still in terms of the dynamic motion of solid molecule, it increases with heating. For liquids, they do not fill a certain container, but it takes a shape the container. And similar to gases, except particles are very closely spaced. Now, for gases they fill a container, taking the shape of the container, but the particles are very widely spaced from one another, and the interparticle interactions are minimal. So gases represent the simplest state of matter. The particles comprising gases are independent of each other and exert very little attraction for each other. As a result, properties of gaseous system can be extrapolated from the behavior of the individual component particles. However, in our discussion on this topic, only the macroscopic properties of gases will be considered. Now, in this slide, so you're asked to um, check your understanding on the concept of gases. So the question is, which of the following statements are true regarding how gases behave? A, gases tend to fill up a container completely. B, gases are difficult to compress. C, gases have definite volume. D, gases assume the shape of the container. E, gases easily diffuse through a tiny hole. And F, gases are heavier than solids and liquids. So the answers here are A, B, and E. So let us try to analyze each one. So A is correct. B is gases are easily to compress. Letter C, so gases, they don't have a definite volume. They depend on the space occupied. D and E are correct. So they assume the shape of the container and they easily diffuse through a tiny hole. F, so gases are lighter than liquids and solids. Now, for perfect gases, so we will be focusing on perfect gases here. So we shall consider a hypothetical perfect or ideal gas, which is a form of matter that completely fills any container. At low pressure and high temperature, so these are the parameters that we will be considering. The density of the gas is decreased and the gas behave or is approaching in an ideal state. So how do we describe perfect gas? So a perfect gas is pictured as a collection of molecules or atom in which it undergoes continuous random motion or what we call Brownian motion. So the speed of the particles increases as the temperature is increased. So molecules are widely separated from one another. So with only interactions being on the side of the container and the other molecules during infrequent collisions. And the molecules or the gas molecules are unaffected by intermolecular forces, let's say dipole-dipole, a van der Waals force. So the physical state of a substance is defined by its physical properties. So for a perfect pure gas, we will be considering these parameters: volume, pressure, and temperature, and the amount of substance or moles. Each substance is described by an equation of state which correlates the variables describing that state. So for example, for volume, if we will be considering volume, so this refers a function with respect to t, v, and n. So let us review each parameter one by one. So you're familiar with the volume. So this refers to the amount of space occupied by gas. So in terms of equation, this is d raised to 3 or cube. So where d is the length of the side of the cubic container. So the SI unit is cubic meter. So what are the other units? Non-SI, we have liter and millimeter. So take note of the conversion. ML is equivalent to cubic centimeter and liter is equivalent to cubic decimeter. Now, if we will try to review known gas laws. So number one is Boyle's law. So it was Robert Boyle, uh, who was an experimental philosopher in the early years of the Royal Society. So he made a very important contribution in developing a description of ideal gas. So you know that Boyle's law relates pressure and volume of gas. So it states that a volume of a fixed gas maintained at constant or fixed temperature is inversely proportional to its pressure. So if the volume is inversely proportional with the pressure, so we could express this as B is related to 1 over P. So if you will express this in terms of proportionality constant, V is equal to KT over P, and then PV is equal to KT. So this is proportionality constant. If we have different conditions, so let's say a given amount of gas at constant temperature is placed under two different sets of conditions, P1, V1 is equal to P2, V2. So thus, it's simply saying pressure of a sample is inversely proportional to its volume. Now, so these slides describe what's the experiment, thousands of experiments that Boyle performed. So with his assistant Robert Hooke. So Boyle and Hooke, so they use a glass J tube to examine the properties of air. So mercury was poured into a column at temperature T, and then air was trapped in a sealed end. So when the pressure exerted by the mercury was doubled, Boyle found out that the volume would be reduced by half. So this slide shows the isotherms. What do we mean by isotherms? So in terms of plots of pressure and volume, so we have what we call isotherms or hyperbolas. So meaning if we plot pressure, Y, as a function of volume X, so this is the hyperbola or the isotherm with respect to increasing temperature. So this represents the graphical representation of the behavior of Boyle's law. So example, in the next slide, if we will plot pressure in terms of the reciprocal of volume 1 over V, so you'll get a straight line. But this shows as as temperature is being increased. Now, if we will rationalize Boyle's law, so Boyle's law could be only applied to ideal gases, very low pressure because we have few molecular collisions and very few interaction between molecules. So as I mentioned before, if you use twice the pressure, what is being expected in the volume? Volume would be reduced into half. Now, let's solve a sample problem. A sample of air occupies a volume of 12.5 cubic decimeter at 30 degrees Celsius when the pressure is 100 kPa. What would be its volume at the same temperature when the pressure is 300 Kelvin? So to solve, so the equation that we will be going to use, since constant temperature, P1, V1 is equal to P2, V2. So the question is, we will solve for the V2 or the final volume. So V2 is P1 V1 all over P2. Substituting 100 kPa multiplied by 12.5 cubic decimeter all over 300 kPa. So the answer is 4.16 cubic decimeter. Another known gas law is the Charles law. So it's a reverse of the Boyle's law. So at constant pressure and amount of gas, so as temperature is being increased, volume would be increased. So in terms of proportionality constant, V is equal to proportionality constant multiplied by T. So Charles' law describes a relationship between volume and temperature at a constant pressure. So, however, if we have constant volume and amount of gas, so its pressure is directly proportional with temperature. So P, so let's change this to P. P is equal to kV at constant volume multiplied by T. So, or on a thermodynamic temperature scale, so divided by Kelvin. So take note that if we will be using Charles' law, we will convert the temperature to absolute temperature. So V1 over T1 is equal to V2 over T2. Now, the variation of volume with the absolute temperature is depicted graphically in this graph. So we call this isobar. So if we will plot volume versus temperature, so notice that we get a straight line here. So lines of constant pressure are known as isobar. So at decreasing pressure, so this is how the graph looks like. So lines, however, if we have constant volume, it's termed as isochore. So this is the plot of pressure versus temperature and with respect to decreasing volume. Take note that pressure falls to zero as temperature approaches absolute zero. So this means that there is no molecular motion that is happening. Now, if we will rationalize Charles' law, so we could say that as temperature is increased, the average speed of the molecule also increases. Therefore, increasing the number and force of the collisions that the molecules have with the container wall. So, but you could only apply it at low pressure. So let's try to solve an example. Sample problem on Charles' law. So we have a volume that contains 20 cubic decimeter of helium at a temperature of 30 degrees Celsius and a pressure of 101.3 kPa. So if the balloon is transferred to a room with a temperature of 20 degrees and the pressure is held at the same value, what would be the volume of the gas inside the balloon? So to solve, so we will be using V1 over T1 is equal to V2 over T2. So substituting, V2 is V1 multiplied by T2 all over T1. So substituting 20 times 293.15 divided by 303. So we will be getting 19.34 cubic decimeter. Now, another law that we will be considering is Avogadro's law. So in order to build up the ideal gas law, we need to consider the relationship between volume and the number of molecules. So when we say molar volume, so this is the volume per mole of molecules. So we could express this as V over N. For any gas, the molar volume is the same, regardless of the type of the gas. So if we will be analyzing Avogadro's principle, it says that volume of any gas is directly proportional to the number of molecules at constant temperature and pressure. So that is the greater the number of moles, the greater will be the volume at a given temperature and pressure. So if we will be converting this to equation, since volume is directly proportional with the number of moles, So V is equal to proportionality constant at constant T and T multiplied by N. V over N is equal to a constant. Therefore, V1 over N1 is equal to V2 over N2. Now, sample problem. So how many moles are contained in a gas sample which occupies a volume of 4.78 cubic decimeter at 273 Kelvin and 101.3 kPa? So actually, this is a direct equation of an ideal gas law, since volume is directly proportional with the number of moles. So N is equal to PV over RT. So substituting 1 atmosphere multiplied by volume 4.78 divided by ideal gas constant multiplied by temperature. So we would be getting 0.2133 moles. So later on in the second part of this video, I'll be explaining the equation of state and how would we apply this to derive the ideal gas equation. Actually, the basis of this ideal gas equation is the combination of Boyle's law, Charles' law, and Avogadro's law.